All right, so this next unit that we're going to start covering is going to cover systems of equations. We're going to start off with some really basic problems, and we're just going to do linear equations first. And then we're going to talk about how we can use some of the strategies that we've used with linear equations, and we're going to talk about how to solve nonlinear systems. So the biggest thing that you have to remember with solving a system is what the solution that you find means. So the solution of any system is just finding where the equations intersect on a graph. So to hammer that point home, what we're going to do is we're going to take the two systems that are here and we're going to graph them. And the solution for the system is just where do they intersect on the graph. Now, whether you solve by graphing, whether you solve using the substitution method, which we'll talk about next, or the elimination method, which we're going to talk about, the answer is going to come out the exact same. They're all going to tell you the same point of intersection. So using this first example here, what I normally do with these is put both equations in slope-intercept form if they're not already. So I'm going to take the top equation and I'm going to subtract 2x from both sides so that I end up with an equation that says y equals negative 2x plus 5. Then I'm going to do the exact same type of thing with the bottom equation. I'm going to subtract 3x from both sides. And then in order to solve that one, I have to divide everything by negative 2. Now, when I divide everything here by negative 2, it's really important that we get all of our signs correct. So I get a y equals, my double negative here is going to give me a positive 3/2 x. And then my positive 4 divided by negative 2 will give me a minus 2. Really important that you pay attention to your signs. So graphing my two equations, if I graph the top one, I'm going to go up to 5. And then use a slope of down 2 and right 1. Now, technically, when you graph a line, you only need 2 points. However, sometimes it is beneficial to add more points. Since we're looking for where the lines intersect, the more exact your lines are, the better chance it is that you're going to see a nice, neat intersection. So I am going to add a couple of more points. So I'm going to go down 2 and right 1 another time, and I'm also going to go up 2 and left 1. So what I end up with is 3 points. And I'm going to use a straight edge to make sure my line is as accurate as it can be. I get my first line. We're going to do the exact same thing for the bottom equation. So if I graph at negative 2, and then go up 3 and right 2 because of my slope, and I end up with a nice, neat point of intersection, and the extra one, the extra point that I just put on the graph, ends up being the point of intersection. So when I graph my two lines, I end up with two lines that look like this. Now here's the important part. Yes, it's very apparent where the intersection is, but in order to solve the system, you actually have to state the point of intersection. So the answer for the question is, what is that coordinate point? And it would be 2, 1. And that's how we're going to solve any linear system. So we could do the next one, but we're going to skip it because I want to get into the algebraic methods. So the next method we're going to talk about is the substitution method. So in order to do substitution, the things you're looking for, I want one of my equations to have a variable that doesn't have a number in front of it. That's how I know that substitution is going to be a good option to use. So when I'm looking at this first problem, number 1 here, I notice that this x doesn't have a number in the front of it. That's a good sign. So what I'm going to do is solve the top equation up here. I'm going to solve it for x. So I'm going to get x by itself. So if I add 2y to both sides, I get x equals 2y minus 6. So what that means is I can now take this 2y minus 6 and I can plug it in for the x down in the second equation. So let's do that and see what happens. Now, when I plug it in, everything in that original equation stays the same. The only thing that's going to be different is that I am going to replace the x that's in the equation with the expression we just found here. So I'm going to put 2y minus 6 in for the x. Now, why does substitution work? Substitution works because now if you look at your equation, it's all in terms of one variable. So I can solve one equation that only has one variable in it. What I can't do is I can't solve an equation that has two variables in it. So in order to solve the rest of this, we're going to distribute. So we get 8y minus 24 plus 6y equals 4. Combining my like terms, I've got 14y's. Isolating my y, I'm going to add 24 to both sides. And to isolate my y, I'm going to divide both sides by 14. So I end up with a nice, neat y value of 2. Now, once I have that y value, I have to go back and find my x value. And I'm going to do that by plugging it back into my equation up here that's solved for the variable I'm looking for. I'm trying to find x, so let's plug the y into the equation that's already solved for x. So if I plug that right in there, if I simplify, I've got x equals 4 minus 6, which is going to give me an x value of negative 2. Now, so we don't lose the entire point of solving a system, what I want you to do is I want you to write all of your answers as ordered pairs. So my x value, my y value. So my final answer for the problem would be the ordered pair negative 2, 2. So please make sure you write your final answers as ordered pairs. One more here. If I solve this one, notice both of the equations have x's with no number in front. So it doesn't matter which one you solve for because they're both going to be fine to do. So I'm going to solve the top equation for x, and I'm going to do that by adding y to both sides. So again, what that means is that y plus 3 is going to take place of the x in the bottom equation. So everything in the bottom equation stays the same, except I'm now going to put y plus 3 in its place. So again, everything stayed the same. The y plus 3 takes place of the x. The rest of the problem is just solved like a normal linear equation. I've got 3 y's total. Isolating my y, I would subtract 3 from both sides. It's going to give you negative 9. And if I divide both sides by 3, I get negative 3. Now again, in order to solve the system completely, you have to take that value and plug it back in so you can find x. And x very neatly, negative 3 and 3 added together, just gives me an x value of 0. Again, so we don't lose the idea that we're still finding where the lines would intersect on a graph, I want you to write them as an ordered pair as your final answer. That ordered pair in this case, x comma y, 0, negative 3. That is your substitution method. Now we're going to talk about elimination. Elimination is called elimination because we have a goal to get rid of one of the variables. We want one of the variables to eliminate. So when I start the problem, I'm looking for either the x numbers to have the same number in front or the y numbers to have the same number in front. The only catch is I want them to have opposite signs because what we're going to do is add the equations together. So I'm actually going to pick to get rid of the y's, and here's why. One of the y's is a 2, one of them is a 4. I can easily get this to be a 4 by multiplying by 2. So I'm going to multiply the entire top equation by 2. So I'm going to double everything. Now, I want those to be the same number, but you can't leave out the other terms. So not only does the 2y get multiplied by 2, but so does the 5x, and so does the 16. So I'm going to get a 10x, a plus 4y, and it's going to equal 32. So what I'm doing here is I'm going to add the equations straight down the columns. Add the x's, add the y's, add the numbers. If I add my x's, nothing cancels out, you just get 13x. If I add the y's, a negative 4 and a positive 4 cancel out. They eliminate. So those are gone. And on the number side, if I add those together, I get a 52. So what I've done is gotten rid of one of the variables, so now the entire equation just has x in it, which is what I want. So if I divide both sides by 13, 52 divided by 13 gives you a value of 4. Now, since we have to find an x and a y, because these are ordered pairs, we have to take that 4 and plug it back in. Now, here's the catch. You can plug this in any of the equations. They're all going to give you the exact same y value. That's the point. So I always plug into the top equation out of habit. It doesn't mean that you have to. It's just what I've always done. It's what I was taught to do in school. Therefore, that's what I always do now. If I multiply the 4 and the 5 here, I get a 20. In order to isolate the y, I'm going to subtract 20. So I'll get a negative 4. And then if I divide by 2, I get negative 2. So again, my x value, my y value. Remembering that this means this is where the two lines would intersect on a graph, I want to write my answers as an ordered pair. So I would write a 4 and a negative 2 as my ordered pair solution. Now, does it always work out, or does it always happen where you only have to manipulate one of the equations? And the answer is no. In the next problem, we would need to manipulate both of these equations. Multiplying just one of the equations by a nice, neat number isn't going to get the job done. So you have to decide which variable you want to get rid of. So since we got rid of y in the last problem, I'm going to get rid of x in this problem. So I want the 7 and the 2 to be the same number, and that can be done by multiplying the top equation by 7 and the bottom equation by 2. Now here's the deal. They're both positive right now. I don't want them to both be positive. I want one of them to be negative. So it doesn't matter which one you select. I'm just going to select the bottom one. There's really no reason why. I'm just selecting to make the bottom one negative. Careful when you distribute your signs. On the top, you'll get a 14x, you get a minus 63y, and a 7. Got to distribute correctly. If I distribute my negative 2, I get a negative 14x, I get a positive 24y, and I get a negative 46. So when I add my columns together, you'll notice that when I add my x column together, they cancel out, which is exactly what I wanted to happen. So I'm going to have those cancel and eliminate like they're supposed to. If I add the next column together, I get a negative 39y. And if I add up negative 46 and 7, I should also get a negative 39, which I do. So the x's are gone. The entire equation just has y in it, which means that if I solve for y and divide, I just get a y value of positive 1. So the numbers looked really messy there for a second, but it ends up falling out to just be a nice, neat value of 1. Now, when I take this 1 and plug it back in, you technically can plug it in either place. I'm going to plug into the top, again, out of habit, into the original equation. So when I multiply those, obviously you get a minus 9. If I add 9 to both sides, you get a positive 10. And when I divide, I get a positive 5. So again, x value, y value. Always write your answers as a finished product ordered pair. And so that ordered pair is going to be 5, 1. That is your elimination method, which is just a repeat of everything you should have learned when you were in Algebra 2. A couple of things we'll talk about next, some special cases. So there are 3 different kinds of answers that you can get for a system problem. You can get a single ordered pair solution, like the 4 problems that we've done so far. Or you can get infinite solutions, or you can get no solution. Maybe the lines don't cross at all. Maybe the lines lay on top of each other. The lines don't cross at all, that would be no solution. If the lines lie on top of each other, that would be your infinite solution case. So let's talk about what they would look like algebraically. Now, if you look at the 2 equations here, notice that they look almost identical. If I were to multiply the top equation by negative 1, I get a negative 3x, a minus 2y, and a negative 10. Now, notice what happens. My x column eliminates, and so does my y column. So on the left-hand side of the equation, all I'm left with is the number 0. On the right side of the equation, I'm left with the number -8. So at that point, since all of the variables eliminate, there are only two possibilities. Either the answer is infinite solutions or the answer is no solution. So your infinite solution case would be if this was a true statement. Now, obviously, this is not a true statement. This is a false statement, which means that this system has no solution. If I were to graph these two lines, they wouldn't ever intersect. Moving to number 2, notice how this one is nicely set up for substitution. It's already solved for y. So I'm going to take that and I'm going to plug it in for the y in the bottom equation. Now remember, when doing that, everything else in the equation stays the same. So let me write that out. And we're going to throw 2x minus 4 into the equation. So remember why substitution works, because now the whole equation is all in terms of x. So if I distribute, I get a 6x minus 12 equals -12. Notice what happens to my x's here. A -6 and a +6 cancel out, and I'm left with a statement that says this. -12 equals -12. So again, when you get all the variables to cancel out, there's only one of two answers it could be, either infinite or no solution. Since this is a true statement this time, this is your case where these are an infinite solution. So what this would look like on a graph is two lines that lie on top of each other. So the reason why we say there's infinite solutions is because when the lines lie on top of each other, they intersect at every single point on the line. So an infinite set of points. Okay, the next part of this is system word problems. So when we're talking about word problems, what we have to do is define variables and then use the variables to write a system. So this is a very common type of problem. So it says a total of $1,200 is invested into two funds. They pay 3% and 5% simple interest. And the yearly interest rate, that's how much money you earn per year in interest, is $500. How much was invested in each account? So let's talk about defining some variables. So I'm going to call the X account 1, and the Y I'm going to call account 2. So let's talk about account 1 and account 2. If you take the amount of money in each account and you add them together, you're going to get $12,000 total. Whether it's split 6,000 and 6,000 or 5 and 7 or 10 and 2, together when you add up all of that money, you're going to get $12,000. Now, how do I use the percentages? Since those deal with interest, that is going to embark or go together with the $500 interest rate. So let's talk about the X account. We're going to say that the 5% account is the X account and the 3% account is the Y account. So every time I throw money into X, I have to multiply it by 0.05 because that's my interest rate. Every time I throw money into Y, I have to multiply it by 0.03 because that's the interest rate. The money that I've earned off my interest is $500 a year. So there is my last equation. Now, in order to solve this, you're going to use one of the methods that we would have talked about previously. Now, whether you use substitution or you use elimination, it really doesn't matter. You technically could also use graphing, but I would doubt that many of you would do that. But you would either select substitution or elimination and finish the problem. Now, I'm not going to because of time constraint, but in your homework, not only will you be asked to write the system like this, but you will also be asked to solve it using elimination or substitution like the previous problems we've done. Okay, so let's talk about a problem that looks like this. It says a department store held a sale to sell off, that should say off, not of, to sell off the 214 winter jackets that remained at the end of the season. Until noon, each jacket was priced at $31.95. At noon, they dropped it to $18.95. Total receipts for the sale were $5,180.30. How many jackets did you sell before noon? So let's talk about the two jacket types. I'm just going to call them X and Y. I'm going to call X before noon, and I'm going to call Y after noon. Now we're going to assume that they sold every single jacket. So there were 214 of them total. So before noon and after noon added together is 214 jackets. Now let's talk about how much money they made off of said jackets. If I sold a jacket before noon, which is X, it cost $31.95. If I sold a jacket, which we're going to call Y, after noon, we sold those for $18.95. Total receipts from the entire day, $5,108.30. So notice kind of a pattern here. We've got one equation that deals with stuff, like how many jackets did I sell, and one that deals with the amount of money that I made. Again, now that the system is written, now you would take this and you would solve it using either substitution or elimination. The choice would be yours, but you would solve it using a method from previously in the video. The second part to this is we are going to talk about how to solve nonlinear systems. So if I look at something like these, where this is obviously not a linear equation, when I graph these, they're not going to be lines on the graph. So we're going to actually graph this one here as the example. We're going to leave this one behind. If I graph this example, the first thing I should notice is the top one is not a line. It is actually a parabola. I'm going to skip the top one for right now, and we are going to graph the bottom one because it's a nice, easy line. So first thing I'm going to do with this, I'm going to put it in slope-intercept form. So I'm going to subtract 2x from both sides, and I'm going to divide the entire equation by -1. So we get a nice, neat equation, 2x plus 1. So a positive 1 and graph up 2 over 1. And again, like I told you on the first problems that we did, the more dots that you draw, the more exact your line is going to be, the better chance of you finding a good, accurate point of intersection. All right, now let's talk about the parabola. Now we've talked about how to graph parabolas earlier this semester, but maybe we don't 100% remember. So first thing, I'm going to get this so that y is by itself. So I'm going to actually move the 7 over and move the y over. So I'm going to subtract 7 and add y. So I get y equals x squared plus 4x minus 7. Now in order to graph this, if you remember, it's in standard form. So the first thing we did was we found the axis of symmetry. Finding the axis of symmetry, negative b over 2a. b is the 4, so I get a negative 4 over 2a. The a is the 1 in front of the x squared, so I get an x value of negative 2. So that means that that value is going to cut my parabola right into mirrored pieces. And we use that value to find the vertex of the parabola, because that's the x-coordinate. If I plug negative 2 in, negative 2 squared is 4. 4 times negative 2 is negative 8. If I take negative 8 and negative 7, and I add them together, I get negative 15. Add that 4, I get negative 11. So there is the vertex of my parabola. So I'm going to come down to negative 2 and come down a little bit past my graph because it only goes to negative 10. That's the very bottom point of my parabola. Now what we did was we found XY table and we graphed. So let's pick a couple points. I'm going to pick, let's say, negative 1, 0, 1, and 2. Now remember, whenever I pick these values, I'm only going to pick them on one side of the parabola because then I can mirror them on the other side. So if I plug in negative 1, 4 times negative 1 is negative 4. Subtract 7 is negative 11. 1 squared is 1, so I get a negative 10. 0, if I plug 0, 0, I'm going to subtract 7. If I plug in 1, 4 times 1, 1, so that's 5, minus 7 is negative 2. If I plug in 2, 2 times 4 is 8, 2 squared is 4, that's 12, minus 7 is 5. Oh, and look at that. I hit right at a nice, neat point. Oops, this shouldn't be on the 0. It should be at negative 2. Sorry. There we go. All right, now, if I draw this half of the parabola, I get my nice, neat intersection. Now, since this is only half the parabola, we also have to graph on the other side. So I'm going to mirror on the other side. This was 1 to the right. I'm going to go 1 to the left. This was 2 to the right. I'm going to go 2 to the left. And it appears that I got a nice, neat intersection point right there. So my answer for the problem is, what are those two coordinate points? This one here is at 2 and 5. That's one intersection. This one here looks like 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7. So negative 4, negative 7. When you graph nonlinear systems, you're likely going to have more than one solution. Do I expect that you still remember how to graph a parabola? Yes, I do. Now let's talk about how to solve some nonlinear systems without graphing. So we are going to stick with doing this by substitution. It's the easiest way to do these. So let's talk about what that's going to look like. First things first. If I solve this equation here for y, I would add 2x to both sides. That means in this bottom equation, that y is going to get replaced with this stuff. So what I'm going to do is rewrite the equation with that taken into account. So in that space that I left, we're going to put this 2x minus 5. Now here's what you don't do. This is not 4 squared plus 25. You have to write this twice, and you have to FOIL it. So if I FOIL that out correctly, you're going to get a 4x squared. You're going to get a minus 20x and a plus 25. Now this one isn't so bad. When I combine my x squareds together, I get 5 of them. My 25s cancel out, so I just get 0. In order to solve this, I'm going to take out common factors. They would be 5 and x. You would be left with an x minus 4. And that's going to give you 2 values of x. If I set that equal to 0, x is going to be 0. If I set this equal to 0, x is going to be 4. Now here's the confusing part. That's not an ordered pair. That's the x values of 2 separate ordered pairs. So you're going to take each one of those and you have to plug them into that right there. And you have to plug in each one separately. So let's talk about plugging in 0. If I plug 0 in, 2 times 0, subtract 5, you get negative 5. Plug in 4. 2 times 4, subtract 5, you get 3. That means that one of the ordered pair solutions is at 0, negative 5, and one of the ordered pair solutions is at 4, 3. Last one, we're going to skip over here to number 3. Now I want you to notice about this. See how these are both solved for y? Since they're both solved for y, that means they're equal to each other. So I'm going to take the top equation, and I'm going to simply set it equal to the bottom equation. You have two things that are equal to the same thing, then they are equal to each other. This now is just a polynomial, so I'm going to get it equal to 0. So if I do that, I'm going to have a single x cubed. If I subtract x squared, I'll have a negative 4 of those. If I add 3x, I'll have a positive 3 of those. And my 1's cancel out. So I get a 0. This has a common factor of x, which I'm going to take out. And then we're going to use our really good factoring skills to factor the parenthesis. Those factors would be x minus 3 and x minus 1. Remembering what we did with polynomials, each one of those gets set equal to 0. So x equals 0. That is going to give you 3. That's going to give you 1. Again, remembering those are 3 separate x values for 3 separate coordinate points. So I'm going to take each one of them and I'm going to plug them into one of the equations. It does not matter which one. However, this one is going to be the easier one because it has smaller powers. So that's the one I'm going to put it into. So I'll have 0 squared, 3 times 0 plus 1. You're going to get 1. Let's put in 3. 3 squared minus 3 times 3 plus 1. 3 squared is 9. 3 times 3 is 9. Those cancel out. Add 1, you get 1. Put in 1. 1 squared. 3 times 1 plus 1. That is positive 1, negative 3, positive 1. 1 minus 3 plus 1. Get negative 1. So, what do my ordered pair solutions look like? There are 3 of them. The first one, we plugged in 0, got out 1. 0, 1. We plugged in 3, got out 1. 3, 1. We plugged in 1, got out negative 1. 1, negative 1. There are your 3 solutions for your nonlinear system. Make note of what questions you have so that you can ask about them in class.